Hello guys, in this video I would like to talk about how to implement your data structure or binary search tree in VEX. And here I'm showing you the inserting new node animation. That is, for each frame I'm inserting a new node into the binary search tree. So the left child will be smaller than the key current node, and the right child will be greater than the current node. So we can see, like this. And this would be a generic data structure. So I'm not necessarily to visualize it, but I could use it for other data processing. And here's how to use it. You have a tree, an empty tree here, we init it, and we can have some points as the key. We have the binary search tree key and value, and we can just insert all the points into the tree. And we could visualize it by using visualize node. This is the tree. We could delete some key, so you just provide some key to be deleted. And we have the new updated tree. And we can also do some range search, that is searching all the key between the range. So yeah, like this. And just like normal data structure, we have minimum, maximum, getting the floor given a key, the ceiling, and compute the height of the tree. And one of the applications I discussed in my previous video is the 2D line intersection problem. Is that given lots of these kind of lines, we wanted to find all the intersected lines. And we could solve this problem by using a binary search tree easily. So before I talk about the implementation, I would like to discuss some of the pitfalls of writing VEX. And so, first I will spend some time talking about VEX. So let's start it. In this example, I use a grid and scale some points, and I write two pieces of code here. Basically, they are the same. We see that I'm just sampling the point using a point triangle and move its position and set the result, right? And this guy is basically the same. But I still, this guy could be interpreted like this. But basically, I would like to talk about how do you interpret it. It's important because in different contexts, we might get unexpected result. So, okay, so for this guy, we all know that Houdini is a data processing node base. So for the node here, we have the P attribute in position, and the node here also has P. And if we are modifying them, basically we have two copies of P, one here and one here, right? So for each node, there might be other position. And what the code here do in this line, 0.0 means is I'm asking what's the P in the node above it, in the zero input. So basically, I'm grabbing the P here. I'm grabbing the P from here and bring it into VEX calculation. So we have a VEX context. And I bring this P into here. And then I just modify it and do some modification. It's called position now. And then I set it to the current context P and the add P. So this P means the current P. So I'm setting the P here, right? So this is how you interpret this code. Okay, so let's see another one. This guy. This guy looks like this. Basically, you should interpret it like this. We have a P here. We have a P here. I'm grabbing the current P, so I'm grabbing this P into the current context, VEX. And of course, I'm doing some calculation, and I got a new variable here, and I'm assigning it to the current context P, right? So basically, it's look like this. It's kind of different because I'm not asking the than the P above it. Okay. But things becomes much more trickier when we are working with the array. First, let's see, I have a detail variable here, and I create a detail attribute called buffer and initialize it a temp variable 1, 2, 3, 4, 5 to 10. And then in this wrangle, let's talk about this wrangle. Okay, so in this wrangle, first I grab the buffer that is in the current context, right? So we have 1, 2, 3 to 10, and assign it to a temp variable. But in every programming language, when we are assigning an array, we are not trying to copy every one of the element. We are just trying to keep the pointer to it. So basically, we are just pointing to the same array here, right? Because it doesn't make sense to, when you are assigning the array, you are doing the whole copy. And here I'm modifying the first element by modifying it as -1, the second one to be -2. And then here's the tricky part. I'm assigning the buffer 0 to the temp2. So I'm modifying this guy. But what is this guy referring to? Is it referring to this context or this context? Is it referring to the array above it? -1, -2, no, 1, 2, 3, 4, 5. Or we are simply referring to ourselves. In this case, we are referring to the node above. So basically, we are referring to this guy. So assigning to it. So this will be the buffer 0 will be the 1, so we assign 1 here. So we get -1, -2, 1, 4, 5, 6, 7. This is basically quite unexpected if you are used to write C++ or other modern programming language, right? So we have to be careful. Yeah. And finally, I just assign the temp to the buffer, change the name back to the buffer. Now let's see another example. The same thing, we have 1, 2, 3, 4 to 10 above, and I'm saying this wrangle. Now I'm grabbing the buffer that is in the, you can say in the current context or the above context, and assigning to call it temp. And I'm modifying it as -1, -2, and setting, of course, itself, the first element, to its third element. So this will be -1. And the result is expected in this case, right? And let's back in Houdini and see another case. It's the same. We got 1, 2, 3, 4, 5 buffer above. And then in this example, here we see that I am grabbing the buffer here and set it into temp and modify the first element into -1, the second element as -2. And then use this add syntax to modify the third element. But as I discussed here, this guy actually means I'm using the asking the information above it. So this is equal to detail 0 buffer 0. And this is much more readable, in fact, because we know that we are reading the position above it, not just using our own, not using this guy to modify this guy. And we just assign it to buffer 2. Everything is expected right now, right? But let me uncomment this code. This is quite absurd. We see that, let me comment, observe here. When what I'm doing in this case is that I'm assigning buffer 0 to buffer 2, 0. But suddenly we see that the whole buffer 2 is changing a lot. You can see it again. I'm only modifying one element, right? That's weird, right? So let's analyze it. Why it will look like this. Okay, so let's analyze it. First, we have 1, 2, 3, 4, 5 to 10 here, and we also have 1, 2, 3, 4 to 10 here. And first, I call the current context to be the temp, right? And I'm modifying the first element as -1 and the second element as -2. So they are gone, they are gone. I'm assigning the element above it to the temp2. So this guy will be 1, right? So far so good. And now I'm assigning the buffer to the buffer2. But the buffer is just the current context, this guy, and to the buffer2. So basically, buffer2 should be this guy, right? Because buffer, this guy just means the current context. Yeah, right? So now buffer2 should be equal to temp. But now I'm adding another new line that is saying buffer0, the current context buffer0. I'm going to assign the element to buffer2 0. But basically what I'm saying is I'm assigning to myself, right? But why suddenly buffer2 change? It's the data above. It's weird, right? So the logic here changed. The buffer here now should be referred to this guy, and we are assigning it to buffer2. And actually we have a copy here, right? So, and you're writing it into this guy. And you're not writing the node above, of course, but you're writing it. There's 1, 2, 3, 4, 5. Of course, we always have a copy at the current node. So this is quite weird, and sometimes we got messed up. We don't know whether we are working in the current context or the above context. And why it would be here? Because in the final line, I'm assigning to the current buffer. And because I have this line, it makes that, it's hard to say, but this buffer0 will refer to the node above it. And this buffer will also refer to the node above it. Yeah, it's kind of like a mess here. You have to think about this. So this will not be my. I don't want you to talk more about this, but what I wanted to say is these codes are a piece of crap. Do not write code like this because it's context dependent. You see that I'm modifying single element, but uncommon this results in the whole change of the array. This is absurd and not tolerable. So what we should doing here is always, if you wanted to get the context from above, you just first we grab the buffer into a temporary variable, and you are working on it. And if you wanted to grab something above it, like specific element something, you should write detail and make it very specific that I want the 0 element of this guy above it. And this guy, yeah. And if you wanted to make sure I want the buffer above it, then you can just keep using temp. And before you modifying temp, you can, yeah. And when you are working done with the temp variable, then finally you assign temp to maybe buffer2 or something else, or buffer3. So what I wanted to emphasize in this case is basically you do not want it to sprinkle like this, something like this in the middle of your code. Okay, so the code will be, okay, so the code should be look like this, something like this. First, I grab the array I needed from the above context, and then I'm working on it. And you won't see I'm using any kind of like VP in the middle of my code or getting an array something like that. They are very unclear and ambiguous. And then once you are working with your array, finally you just use set detail attribute to set the result. I think this is the most cleanest approach, especially if you are working with array. For point attributes or for single integer, sometimes it's fine, but sometimes you might still get an unexpected result. It's not like using modern C++ programming. Okay, so enough with the pitfall of the VEX. These are all short codes. Just don't try to write code like this. Okay, so now what I wanted to talk about is some performance issue. I have a grid here, and I schedule some points. And now what I wanted to implement the binary search tree. But the question is, where can I store my data? Where can I allocate my memory, just like modern programming language? Should I store my data into the point or using an array in the detail? Right? So first, let's try the detail. I create a detail array node, call it as node, and initialize it. I'm just pushing lots of zero inside. Sorry for bad practice. I should write something like this. This will be better. Yeah, as I said, don't try to sprinkle this in the middle of your code. Oops. And finally, you have to assign it back. So first I initialize some zero inside it, and then I just set some points to be -1 by using a rand. And yeah, and in this case, I'm also creating a node, but this time I'm creating the attribute on point rather than storing them as array here. And I'm also modifying them by using setPoint attribute with random. So what should we do? Should we build our binary search tree here or here? In practice, you could do both, but there is some kind of performance difference in Houdini, so let's benchmark it. And I'm going to use 200,000 points here. And immediately we see the difference, that we see that pushing into this array is very slow. And when you are using the random access of the array, it's going to be very slow too. Don't talk about initialization because it's unfair, because we also have to create some points. But let's see the direct access of the array by setting the elements to -1. It took 0.3 seconds, and for point, it's only 0.05. Obviously, we should build our binary search tree here rather than using the array. And here's the conclusion. Do not try to store large amount of information into the array and working on it. And yeah, it's better to work on points. I don't know why. I'm guessing that because in Houdini, the point in internal memory might use some kind of hash with the ptnum. I don't know. I'm not a Houdini engineer. But the fact is, the array here is very slow. Okay, let's talk about another problem. It's race condition. Many people have ignored or don't understand. Again, I prepare some points, and for each point, I'm setting its ID and a message called "Hello, I am my ID." Alright, and I randomly sort the point. Now here's the race condition code. I use a point wrangle, that is for each point that this code will be run. I'm setting point attribute on the first point. So basically this point. But every point is running this code, is writing to it. So we don't know who will be the last guy writing to it, right? Because there are others that will also write to it. But it will be overwritten by the other points. So you have to be very careful if you are using point triangle primitive vertex and you are setting the attribute of others. You are not setting attributes of yourself. We are not setting attributes like ptnum, then everyone is writing to itself. But if we are setting attributes to others, we have to be careful of the race condition. Race condition is we have two different guys. They are trying to writing to the same destination, but the order is not. You don't know. Yeah, this is a problem. Except you don't care about it, but you have to be careful. Yeah. But if we are trying to build a binary search tree into the point attribute, if we're going to store the node information into the point, we will have another problem, and I'm going to show you now. So I'm using a point triangle here, and what I wanted to do here is that for each point I wanted to modify the other guy's information. First I will initialize a variable called id, and it will be ptnum. I'm going to use another point triangle, and that is okay, let's just work on point 3 only. So this code will only run on point 3. And for point 3, I wanted to modify the value of point 4, okay? So let's say if I need to, I'm doing some, first I'm going to get in the point 3 position, and I'm just modifying it and setting it into the attributes of the point 4 and using the plus like this. So we see the point 4 has been updated, right? Before, after. But the problem here is if you try to read the information from point 4, let's call it point 4 position, and let's just assign it to our current position. We see that we are not reading the new information because, as I discussed earlier, what this guy do is you're reading the information above it. So this is before the point 4 has been updated. So even though you set the attribute to others, you can't read it, and there is no way in Houdini to read it. You can only, except you're reading your current position point 3. You can only write to your the current point we are working on. But for other point like point 4, point 5, you can only read the information above you. You cannot read the information you just updated here. So it will be very hard to code a binary search tree if we need to set something, like we set something to point 4, and then I need to read it later. Maybe there are some other code here. And if you wanted to read it here, you're reading the wrong information because you're reading the old information. So you have to keep this information and use it here. Just like you can use this. You have to use this position here. So it will be very hard to code, especially a really complex data structure like binary search tree. Binary search tree is okay, but for red black tree, it will be really, really hard. But for binary search tree, basically, we don't have this problem, so it's okay. Just have to be careful. Okay, but if we were working on the detail attribute, we have done this problem because basically we can read it, write it in the middle of the code. So actually I implemented both type of the binary search tree. So in this type, you see all the attributes are in the detail. And basically you can see I'm using the array access. And I'm also setting the result, modifying the array directly and getting the information from it, which I can just read write in the current context. It has nothing to do with the above context. But if we are going to store the attributes on point, we have to be careful. So in modern usual programming language, when we are coding a binary search tree, we will have the key and then maybe the value, but we also need a reference to its left child and right child, and maybe its parent. And the reference or pointer basically is just a memory address. But in VEX, we don't have it. So if I'm going to store the for each point, I'm going to see it as a node, as a binary tree node. I'm going to design a way kind of like the pointer or reference, and it's very easy. We can just use the point number as the memory address. So it's like, let's see this example. Oops, wait. Okay, so now I have a binary tree here, and it has just a node. And I will use the point number as memory address and create point attribute left, right, parent. And -1 just means no pointer. They are not pointing to anyone. And I'm going to insert another node here. So I insert a second node here. So the first guy, the first guy left is now 1. It's pointing toward the PT1 point. And it's this guy storing the key, and its parent is the 0 point, and its left right is no node. Yeah, so we could use this method to kind of design a pointer memory address. But what about the deletion? Because if we wanted to delete some points, we can't actually delete that point from the point list. Because if we delete it, we are messing up our memory address. So we are just doing some, you can see that after the deletion, I still have the same amount of points. I'm just modifying the left-right pointer to the newly pointed node, and all the deleted nodes will just be tagged by a group. They are dead now, so no one is pointing to them. And I'm also using an array here. So when I am inserting a new node, first I will search, is there any point I could reuse? They are being deleted. So the code will be look like this. Let's see. So for the insert, here I just grab the detail attributes, and this is the empty slots. That means that is the node I deleted, and they can be reused. It's like, oops, wait a second. Yeah, it's here, the empty node. So we are reading if there is any points we could reuse. And then we are just grabbing the key and the value to be inserted and insert it into the tree. So for the insertion, we see that if we use create node, it's kind of like the new in C++. And let's see. So we have a create node, and first we check if we have any slots we could reuse. If there is one, we just return the point number. It's like memory address. And if we don't have any point to be reused, we could just create a new point and return its point number as memory address and initialize it. And for other kind of operation, it's just a normal binary search tree operation. For example, let's see the insertion code. So let's see the put. So for put, we simply first create a new node. It may be the memory from the recycle points, the reuse points, or the newly created points. And we just have to find the slots to be inserted. So this is just normal binary search. We go left, we go right. Yeah, just normal binary search, left, right. And then once we have got the correct point, we have to set its the left child or right child. Yeah, and when we are creating calling this create node, we are also setting its new parent. So yeah, everything is linked up. And let's see about the delete. And yeah, for delete node, first we have to find the node to be deleted. So it's basically the same. We're just going left or going right, and then return the memory address, the point number to be deleted. And if we found it, we then just binary tree delete. We have to reset the left right parent and this kind of attributes. Because I'm not doing a binary search tree algorithm data structure course. This is I think everyone who know binary search tree know this. And we have to be careful that we are not setting some attributes and then reading them back, because as I said previously, that you will read the wrong information. You are not reading the latest information you are setting. And let's see, the find keys between low high is just the same. We are just go left, go right, go left, go right, and then just setting the point we found to a group, so we know which kind of tree nodes are within the range. So these are all standard binary search code. Yeah. Another thing worth mentioning is the visualization of the data, because basically we're just working with all these points. But if we wanted to visualize it, to really construct it, something let's talk about. First up, we will create this kind of pattern. We will setting each point to their correct position, and the algorithm is quite simple. It should look like this. Yeah, the plot trees, and it looked like this. Basically, we are doing the in-order traversal of the tree. So this is the root. Then we will go down, and we have a direction to go down, right? And then for in-order traversal, we will have to go left, and then we will trace back, and then go right. So for each step, we just have to rotate our direction, and then so for each step, it's kind of we will need to use a stack for in-order traversal, and we will store the current position, and the direction to walk to, and we will also store just the current node position and direction. And if we are going left, we will just use a matrix to rotate our direction by an angle. And then if we are tracing back, we are also pushing this, we are storing our position direction to a stack. And if we are tracing back, if we are finished with here, so we will pop the position direction. So we could get back our position direction. And then we will just rotate right to go right. Yeah. It's basically in order traversal, but with the position and direction. Yeah. So we have our input node here with all the data, and I just set the angle for each turn, and for each step, how long should I walk? It should this I just have a angle and a step, so that yeah, so we have an angle and a step here. So for each step, we simply use a matrix, rotation matrix, to modify our direction and update our position, and go left and go right. And we could get this pattern, the points. And then we just have to form the primitives. And it's extremely easy. We just have to form, because we have the left right child, we just have to add the primitive to the left and a polyline to the right. Yeah. So we have a tree here, and we can visualize it. Just maybe we could use a font to show the key, because we have information inside the key, the point, and maybe set the color by the relative position, just for so we can visualize it. Create a visualizer of the tree. Yeah, it look like this. Yeah, like this. Or I should hide the Visual Studio. And yeah, we could, let's say I wanted to insert lots of 30,000 points here. It's quite fast, and we see the result. We have a tree here. Yeah, and personally, I think it's quite beautiful. Yeah, so yeah, we can change the seed. And we know that for binary search tree, the insert key should be randomized. So if we just, there's some bad guy who just insert by a sorted attribute, we will get a degenerated tree like this, and it's quite interesting to see the degenerated tree. Yeah, so this is the binary search tree.